Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine ABCD constants of a three-phase medium length transmission line based on its nominal pi equivalent circuit. We shall also learn how to calculate percentage voltage regulation and efficiency of transmission of this line using those constants. Using nominal pi equivalent circuit, we have to determine the sending end voltage, current, power factor and input power of a three-phase 50 Hz 161 km long transmission line delivering full load of 50 megavolt ampere at 132 kilovolts and 0.8 power factor lagging. We also have to compute the efficiency of transmission. Given resistance per kilometer per phase 0.157 ohm and conductor diameter 1.96 centimeter with spacings 3.66 meter, 6.4 meter and 7.32 meter transposed. We also have to evaluate the constants A, B, C, D and calculate the receiving end voltage regulation. Let us first write down the given data. Load SL equals to 50 megavolt ampere, that is equal to 50 into 10 to the power 6 volt ampere. Line to line receiving end voltage VR line equals to 132 kilovolts, that is equal to 132 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 132 into 10 to the power 3 divided by root 3. That gives us 76,210 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now determine power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for load SL equals to root 3 times VR line into IL. Therefore, load current IL equals to SL divided by root 3 times VR line. Using values we get 50 into 10 to the power 6 divided by root 3 into 132 into 10 to the power 3. That gives us 218.7 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 218.7 ampere at an angle minus 36.8699 degree. Here load current IL equals to receiving end current IR. Let us now calculate power delivered to the load. PL equals to SL into cos phi L. Using values we get 50 into 0.8, that is equal to 40 megawatts. Given length of the transmission line D equals to 161 kilometers. Diameter of the conductor D1 equals to 1.96 centimeter. Let us now calculate radius of the conductor. R equals to D1 by 2. That is equal to 1.96 divided by 2. That gives us 0.98 centimeter. Spacings between the conductors D12 equals to 3.66 meter, D23 equals to 6.4 meter and D31 equals to 7.32 meter. Let us now calculate equivalent equilateral spacing between the conductors. DQ equals to cube root of D12 into D23 into D31. Using values we get cube root of 3.66 into 6.4 into 7.32. That gives us 5.5555 meter or 555.55 centimeter. Since the conductors are transposed, expression for inductance per kilometer per phase L1 equals to 0.05 plus 0.2 into log of dq upon r millihenry. Using values we get 0.05 plus 0.2 into log of 555.55 upon 0.98 millihenry. That gives us 1.318 millihenry. Let us now calculate inductance per phase. L equals to L1 into D. Using values we get 1.318 into 161, which is approximately equal to 212.2 millihenry or 0.2122 Henry. Expression for capacitance per kilometer per phase C1 equals to 1 upon 18 into log of dq upon r microfarad. Using values we get 1 upon 18 into log of 555.55 upon 0.98 microfarad. That gives us 0.00876 microfarad. Now we shall calculate capacitance per phase. C equals to C1 into D. Using values we get 0.00876 into 161. That gives us 1.41 microfarad or 1.41 into 10 to the power minus 6 farad. Given resistance per kilometer per phase R1 equals to 0.157 ohm. Let us now calculate resistance per phase R equals to R1 into D. Using values we get 0.157 into 161. That gives us 25.277 ohm. We have computed inductance per phase L equals to 0.2122 Henry and capacitance per phase C equals to 1.41 into 10 to the power minus 6 farad. Let us now calculate inductive reactance per phase XL equals to 2 pi F into L. Given supply frequency F equals to 50 Hz. Therefore, XL equals to 2 pi into 50 into 0.2122. That gives us 66.6646 ohm. Capacitive susceptance per phase BC equals to 2 pi F into C. Using values we get 2 pi into 50 into 1.41 into 10 to the power minus 6. That gives us 443 into 10 to the power minus 6 mho. Series impedance per phase of the transmission line Z equals to R plus JXL. That is equal to 25.277 plus J times 66.6646 ohm. This may be written in polar form as 71.3 ohm at an angle 69.235 degree. Shunt admittance per phase Y equals to J times BC. That is equal to 0 plus J times 443 into 10 to the power minus 6 mho. This may be written in polar form as 443 into 10 to the power minus 6 mho at an angle 90 degree. We have obtained series impedance per phase of the transmission line Z equals to 71.3 ohm at an angle 69.235 degree and shunt admittance per phase Y equals to 443 into 10 to the power minus 6 mho at an angle 90 degree. Let us now calculate Y into Z. Using values we get 443 into 10 to the power minus 6 at an angle 90 degree into 71.3 at an angle 69.235 degree, that gives us 0.0315859 at an angle 159.235 degree. This may be written in Cartesian form as minus 0.029534 plus j times 0.0111983. Now we shall calculate 1 plus 1/4 of y into z, that is equal to 0.9926 plus j times 0.0028. This may be written in polar form as 0.992604 at an angle 0.1616 degree. For pi equivalent circuit, A equals to D equals to 1 plus half of y into z, that is equal to 0.985233 plus j times 0.0056. This may be written in polar form as 0.98525 at an angle 0.326 degree. B equals to Z, that is equal to 71.3 ohm at an angle 69.235 degree, and C equals to Y into 1 plus 1/4 of y into z. Using values we get 443 into 10 to the power minus 6 at an angle 90 degree into 0.992604 at an angle 0.1616 degree. That gives us 439.72 into 10 to the power minus 6 mho at an angle 90.1616 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 76,210 volts at an angle 0 degree. We have obtained receiving end current IR equals to 218.7 ampere at an angle minus 36.8699 degree, and generalized constants for pi equivalent circuit A equals to D equals to 0.98525 at an angle 0.326 degree, B equals to 71.3 ohm at an angle 69.235 degree, and C equals to 439.72 into 10 to the power minus 6 mho at an angle 90.1616 degree. Expression for sending end voltage per phase Vs equals to A times VR plus V times IR. Using values we get 0.98525 at an angle 0.326 degree into 76,210 at an angle 0 degree plus 71.3 at an angle 69.235 degree into 218.7 at an angle minus 36.8699 degree. That gives us 88,255.641 plus j times 8,774.5117 volt. This may be written in polar form as 88,690.756 volt at an angle 5.678 degree. And expression for sending end current per phase Is equals to C times VR plus D times IR. Using values we get 439.72 into 10 to the power minus 6 at an angle 90.1616 degree into 76,210 at an angle 0 degree plus 0.98525 at an angle 0.326 degree into 218.7 at an angle minus 36.8699 degree. That gives us 173 minus J times 94.79 ampere. This may be written in polar form as 197.267 ampere at an angle minus 28.719 degree. On no load receiving end current IR equals to 0. Therefore, receiving end voltage per phase on no load VRO equals to Vs divided by A. Using values we get 88,690.756 at an angle 5.678 degree divided by 0.98525 at an angle 0.326 degree. That gives us 90,018.529 volt at an angle 5.352 degree. Let us now calculate voltage regulation, that is equal to VRO minus VR divided by VR. Using values we get 90,018.529 minus 76,210 divided by 76,210. That gives us 0.1812 per unit or 18.12%. We have computed sending end voltage per phase Vs equals to Vs at an angle delta equals to 88,690.756 volt at an angle 5.678 degree, and sending end current per phase Is equals to Is at an angle minus 51 equals to 197.267 ampere at an angle minus 28.719 degree. For star connected system, sending end current per phase equals to sending end line current, and line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 88,690.756, which is approximately equal to 153.62 into 10 to the power 3 volts or 153.62 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 5.678 degree plus 28.719 degree. That gives us 34.397 degree. Let us now calculate sending end power factor. Cos phi s equals to cos of 34.397 degree. That gives us 0.825 lagging. Now we shall calculate sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 88,690.756 into 197.267 into 0.825, which is approximately equal to 43.3 into 10 to the power 6 watts or 43.3 megawatt. Now we shall calculate efficiency of transmission. Eta T equals to PL divided by PS. We have computed power delivered to the load. PL equals to 40 megawatts. Therefore, eta T equals to 40 divided by 43.3, that gives us 0.9238 per unit or 92.38%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine ABCD constants of a three-phase medium length transmission line based on its nominal pi equivalent circuit. We have also learned how to compute percentage voltage regulation and efficiency of transmission of this line using those constants. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.